So we've been talking about magnetic vector potential. I've got an example here. A current distribution gives rise to the vector magnetic potential A, given by that thing there, Webers per meter. Calculate, okay, the flux density at a certain point, and part B, the flux through the surface given by that thing there. All right, so let's get started, and we'll of course start with part A. So we're looking at the flux density at a certain point in space. So let's remember that the flux density is the curl of the magnetic vector potential. Alright, so I'm going to set this up. This is the determinant of AX, AY, AZ. Then the del operator is d dx, d dy, dz, like that. And then the vector magnetic potential is x squared y, y squared x, and a minus 4xyz. Now, I'm not going to work out the details of this curl. By this point in the course, you should be very comfortable computing this determinant, computing a curl. And so when we do that, we get 4xz in the x direction, minus 4xz in the x direction, plus 4yz in the y direction, plus the quantity y squared minus x squared, all of that in the z direction. So pause the video if you want, try to get that on your own, but again, I'm not going to show those details. Now, we want to get the flux density at this certain point, right? X equals minus 2, y equals 2, z equals 5. So we just plug those guys up in there. So we say we've got negative 4 times negative 1 times 5 in the x direction, plus 4 times 2 times 5 in the y direction, plus looks like 2 squared minus negative 1 squared in the z direction. Okay, so we compute that, and we've got 20 in the x direction plus 40 in the y direction and 3 in the z direction. And again, the units of flux density is magnetic flux density, that is Webers per square meter. Right, so that's our answer to part A. Moving on. Part B, we're going to calculate the flux through the surface given by that. So let's first plot the surface, and you'll notice that z does not change in our surface, so we really can plot this in two dimensions. So this is going to be y and this is going to be x, and we know that x goes from 0 to 1 and y goes from negative 1 to 4. So what we're dealing with is this surface here. Okay, so this would be 4 up there, negative 1, and of course we're going from 0 to 1. So we're talking about this surface. It's not in the yz plane. It's in the plane z equals 1, but it's kind of projected that way. We can get a good visual on it. And then we're dealing with the surface vector. Remember, the surface vector points perpendicular to the surface, so the surface vector is coming out towards us there. S is the surface vector. Alright, so we're going to solve this in two ways, and the first way is just kind of the definition of flux, and so we're going to take the flux density, right, and dot it with ds and integrate over the surface. So we calculated the flux density, that's this thing here, right? And so the x component is negative 4xz, and the y component is 4yz, and so forth. But I'm just going to write it. I'm going to save myself some time, and I'm just going to write it like this. I'm going to say, yeah, there's an x component. Yeah, there's a y component. Yeah, there's a z component. And the reason I'm doing that to save time is going to be evident soon here. And then the ds, so this is the change in surface. So you ask yourself again, what is changing in my surface? Well, x is changing and y is changing. Z remains constant. So this is dotted with dx, right? dy, and then we already said the surface vector points towards us in the z direction. So the reason, see, I wrote it as bx, by is because they actually drop out when we do this dot product, and we just get over the surface, which is going to be a double integral of the z component, right? Because az dotted with az is 1, bz is y squared minus x squared, and then dx dy, and now I'll put the bounds on, so dx, x's go from 0 to 1, and y's go from -1 to 4, and I'll put the labels there. Y is going from -1 to 4, x is going from 0 to 1, like that. Okay, so now I just do this straightforward integration, so I'll work with the x's first, so we'll leave the y's alone. So when I do the x's, I get a y squared x minus 1/3 x cubed, evaluated from 0 to 1, and then I still have dy. So this gives me, again, y's go from -1 to 4. So I get y squared minus 1/3, it looks like, then dy. Alright, so now I integrate that with respect to y, and I get 1/3 y cubed now, minus 1/3 y, evaluated from -1 to 4. And when I plug in the bounds and simplify, I get 60 over 3, which is 20 Weber. Alright, so that was one way of doing that. So I want to show two different ways. So we'll say that was kind of part one, and I want to emphasize here that that is the answer. So if you were just instructed to find the flux, you've got the answer there correctly. But now we're going to do it in a second way, and we're going to apply Stoke's theorem to our integral. So Stoke's theorem relates a surface integral to a line integral, and in this case to the vector magnetic potential. So what we can do is we can say that the flux then, using Stoke's theorem, is equal to the line integral over the closed path, right, of A dot dl. Okay, and the way we're going to calculate that integral is to separate this path into 4 sections. So we're going to go this way, this way, this way, and then this way. And we have to be careful of the direction there according to the right-hand rule. So we're gonna swirl around our s vector, so we have to swirl it around such that when we curl our fingers around s vector with our right hand, our thumb points to the direction of the z-axis. So that's the direction that we're going to choose. That's the direction that we're going to go around that path. Okay, so for section 1, right, section 1, we ask ourselves again, what is changing? Well, as I go from here to here, only y is changing. So y changes, so that means that dl in this case, dl in this case is just dy ay. Okay, so now all I need, and after I do this dot product, all I need is really the y component of a. Okay, so I'm not going to show the details here, but you should know that when I dot ax with ay, I get 0, and when I dot az with ay, I get 0. So the only thing I need here is a y dotted with ay, so I need the y component of a. So this integral then would reduce to y equals, we're going to go from 4, so the direction matters, 4 to 1, -1. And then we have y squared x, which is the y component of a, and then dy. And actually, since x is a constant on this path, segment 1, and x is being held at 0, then actually this just integrates to 0. That's because x is 0 on that segment. Okay, so now we do segment 2. So we ask ourselves, what is changing when I walk along segment 2? X is changing. X goes from 0 to 1. So dl would be dxax in this case. And so we would have something like this. So the x's go from 0 to 1. And then again, when I do the dot product with a, all I pick out here is the x component. So I've got x squared y dx, like that. And so when I do that integration, okay, this becomes 1/3 x cubed y from 0 to 1, right? And y here is 4. No, excuse me. Y here is -1, right? -1. So when we do that, we get -1/3 Weber, right? All right, so now I'm going to do segment 3. So segment 3, I ask myself, what is changing when I go from down here to up here? What is changing? So it's the y's that are changing again. So what I can do here is just say, again, dl is dy ay. So when I dot it with that, that just picks out the y component again, similar to segment 1, excuse me. So now I've got y goes from -1 to 4, the direction matters, of just the y component, y squared x dy. But this time, I'm not going to get 0 because x is at 1 now on our surface, right? X is at 1. So when I do this, when I plug in x equals 1, and then I just integrate with respect to y, this is 1/3 y cubed, and I plug in the bounds, I get 65/3 Weber. Again, that's with x equals 1. Okay, and I'm going to do segment 4 up here in the top right. Segment 4, I ask myself, what is changing when I go from this point here to this point here? Okay, and it's the x's that are changing. So again, I'm going to pick out the x component here. And so this will be x goes from -1 to 0, right? Picking out the x component, so x squared y, right? When I do the dot product, dx. And y is now at 4, so this is, you can think of this as, well, when I do the integration, this is 4/3 x cubed from -1 to 0, like that. And so what I get here is -4/3 Webers. And again, that's with y equals 4. Okay, so my total flux is the sum of those, this guy, and this guy. So -4 and -1 makes -5, plus 65 makes 60/3. So 60/3 Webers, that's what we had here, right? And that's, of course, 20 Webers. And so that's our final answer. And of course, it has to match what we did in the first part before we used Stoke's theorem.